Alright, welcome to topic 8, Thermodynamics. Okay, so let's go ahead and get started. So thermodynamics is going to encompass a few different parts. So we're going to begin with part 1, thermochemistry, and from thermochemistry we'll have a look at heat capacity, specific heat capacity and calorimetry, and also endothermic, exothermic reactions, thermochemical equations, Hess's law, and also the standard heats of formation. Let's consider for a minute the flow of energy in the biological world. So we know that sunlight is the origin of biological energy. All of the energy on the planet comes from the sun. Okay, so energy of sunlight arises from nuclear energy, where part of the enormous energy in the hydrogen atom is released on fusion. Okay, so there's a fusion reaction that's ongoing in the sun, and this releases energy. Now the gamma radiation is absorbed by electrons, and it's emitted as photons of light energy, and this is going to then travel to the Earth as radiant energy as well. Okay, and one of the main parts of the biological systems of the world, so what kind of life form benefits most immediately from this, obviously, are the plants. Okay, so the green plants are able to undergo photosynthesis. And in this photosynthesis, these plants will use carbon dioxide and water, and they'll produce oxygen and carbohydrates. Okay, and we know that some plants even produce proteins as well that we can use as a food source, so carbohydrates in the most part. Alright, and then the animal world can then use this chemical energy that comes from the plants. So we can eat the plants, and other animals can eat the plants, and some animals eat other animals, but it's all coming from the sun ultimately. So the sun is going to produce these carbohydrates, for the most part, that the animal world uses as chemical energy through the process of respiration to do biological work. Okay, and thus we have an increase in entropy, and we'll discuss entropy soon and what this really means. Okay, so this is the flow of energy in the biological world, but you can see it all starts with energy that comes from the sun. So what is thermochemistry? So thermochemistry is defined as the study of heat changes in chemical reactions, and it constitutes a section of the wider study of energy and the interconversions of energy called thermodynamics. So thermochemistry is part of thermodynamics. Okay, so it's just looking at the heat changes in a chemical reaction. It's very simple. So energy is the capacity to do work or to produce heat. Work is done when a force is displaced. So work equals Fs, where F is force and S is displacement. So force is defined as mass by acceleration. Okay, so when we're able to, if we move an object across the desk, for example, if we move an object across the floor, then work is being done. So we've displaced a force. Heat is the flow of energy from an object at a higher temperature to one at a lower temperature when the two objects are in thermal contact. Okay, and temperature is related to the random motions of particles of a particular solid, liquid or gas. So by measuring the temperature of a solid, or liquid or a gas, we can get an idea of the motions of the particles in that solid. If the particles are moving faster, then it's going to have a higher temperature. Okay, or if they're vibrating faster or what have you. The interesting thing about heat is that it has to flow from an object to another. It can be produced chemically as well in a chemical reaction, but it has to come from somewhere. So you can't get heat for free. Let's move along to the laws of thermodynamics. There are 3 laws of thermodynamics that we'll consider. First of all, the law of conservation of energy. So this states that the energy of the universe is constant. So energy cannot be created or destroyed, but it can be converted from one form to another. Okay? So we can't create energy from nothing. It has to come from somewhere. So think about that energy from the sun. It's actually coming from a nuclear reaction of those hydrogen atoms. In the time spans that we can consider, that energy has to always come from somewhere. It cannot be created or destroyed. In any spontaneous process, this is law number 2, in any spontaneous process, there is always an increase in the entropy or the randomness of the universe. Or more generally stated, the entropy of the universe is increasing. So the disorder or the randomness is always increasing of the universe, okay? The idea is that in any system and in the universe is that entropy or randomness is always increasing. And law number 3, entropy of a perfect crystal at 0 Kelvin is 0. So in other words, at absolute 0, that motion will stop. So entropy is a measure of randomness or disorder. Thermochemistry is concerned with the application of the first law of thermodynamics to chemical and physical processes. And the second and third laws involve entropy and the spontaneity of chemical and physical processes. The laboratory process of measuring heat change is called calorimetry. So we can actually measure the heat change in a reaction using a calorimeter, and this is called calorimetry. And this is where the word calorie comes from. It's a measure of energy. So the universe is divided into 2 parts. So we've got the system and we've got the surroundings. Okay? Now the universe is defined as being the system and the surroundings. So in chemistry, the system is just the reactants and the products, and everything else is the surroundings. So the container that you actually mix the reactants and the products together in is the surroundings, okay? And also everything around it is the surroundings as well. If you imagine you're doing a small reaction in a test tube, so it's just the reactants and products that are your system, and everything else is the surroundings. Even the solvent that's in there can be the surroundings because it's surrounding those reactants and those products. And heat can be transferred into the test tube, or it can be taken from the test tube. So the test tube might feel warm or it might feel cold, depending on the reaction that's being performed. And everything, so the test tube, the reactants, the products, the solvent, and everything around it is considered to be the universe. So the internal energy of a system is the sum of the kinetic and potential energy of all the particles of the system. Okay, so internal energy. So the system just being the reactants and products, if you sum the kinetic and potential energy, you get the internal energy. And the internal energy of a system can be changed by the flow of heat, work, or both. Okay, so heat is our little lowercase q, and work is our lowercase w. So the internal energy of a system, right, the change in the energy is going to be heat and work. So the system can be a closed system, and it exchanges heat with surroundings. It can be an open system, and it's going to exchange its heat and its mass with the surroundings as well. And an isolated system has no exchange with the surroundings. So it can be closed, open, or isolated. So closed is closed. Imagine a test tube with a stopper on the top. Okay, it's closed, but heat can still be exchanged with its surroundings. Thermodynamic quantities consist of 2 parts. First of all, a number, which indicates the magnitude, and a sign, and this indicates the direction of the flow from the system's point of view. It's always from the system's point of view, so it can be positive or negative. So if energy flows out of the system via heat, then Q is negative. So Q is our heat. So if it's negative amount of heat energy, then it's an exothermic reaction. It's giving off heat. Okay? So the energy of the system is decreasing. If energy flows into the system, then its Q is going to be positive, so it's going to be endothermic. It's going to feel cold to the touch. It's going to be taking heat from its surroundings, so we get a positive value for heat, okay, from the point of view of the system. And you can see the diagram. There's our exothermic process giving off energy, and our endothermic project is absorbing. Our endothermic process is absorbing energy in the form of heat. So energy, remember, is the capacity to do work or produce heat. And this is actually a state function. Now, we haven't really covered what a state function means, but a state function is certain, if you think of certain quantities, they can be a state function. So for example, altitude is a state function. So the thing about altitude is, if you're at a certain altitude, that's a fixed value. It doesn't matter how you got there. So if you're climbing a mountain, it doesn't matter if you were dropped on the top of the mountain using a helicopter, or if you walked up the side of the mountain, you're still going to be at the same altitude either way. So the path you took doesn't matter. And energy is a state function as well, because a system has a certain amount of energy, and it doesn't matter what the overall path was, whether the system absorbed some energy, then it released some energy, and then it doesn't matter. If it's a certain level of energy, it doesn't matter how it got there. Okay, it's a bit like altitude or temperature. It doesn't matter how it got there, it's not going to affect the overall energy of the system. So energy has no memory of history, in other words, and that's what a state function is. So energy is the capacity to do work or produce heat. Oh, here's our definition of state function: determined by the state of the system regardless of how that system was achieved. Okay, so the path doesn't matter. When the state of a system changes, the magnitude of the change in any state function is proportional to the initial to the final state, not on how the change was accomplished. So we just look at the initial state and the final state. So if we think about our altitude example, okay, the altitude difference from the base of the mountain to the top of the mountain is going to be a fixed value. It doesn't matter how you climbed to the mountain, what path you took, the altitude difference is going to be the same value. And that's what a state function kind of is. Okay? So when we look at energy differences, it doesn't really matter what path we took, the amount of energy change is going to be the same. So there's two main types of energy that we'll discuss. There's potential energy and there's kinetic energy. So potential energy is energy related to the position or the composition. So we could have, for example, water behind a dam. It's converted to work when the water flows down through the turbines, but when it's just sitting behind the dam, it has potential energy. Okay, or we could have chemical energy. So you've got a battery, but nothing's actually connected to the battery. So you've got potential energy sitting there. Okay, or attractive or repulsive forces, or you might just have a book sitting on the edge of the desk. And if you were to push the book off the edge of the desk, it will fall. But when it's sitting up elevated, it has potential energy. It's got the potential to do work. Then we've got kinetic energy, which is due to motion. So this is energy in process. So as the book is falling off the desk, it has kinetic energy. This is energy which is to do with mass and velocity. Okay, and this includes work and it includes heat. So here we have enthalpy. Enthalpy, capital H, equals energy plus PV, where P is pressure and V is volume. So since energy, pressure and volume are all state functions, enthalpy, H, is also a state function. Now a change in enthalpy, delta H equals delta E plus P delta V, because the pressure is held constant. And note that delta H, our change in enthalpy, equals delta Q, which is our change in heat, okay, at constant pressure. So in a way, enthalpy really is heat. You know, you can think about enthalpy as being a heat energy. So delta H equals delta Q if the pressure's held constant. Okay? So at a constant pressure, delta H equals our energy flow as heat. And for a reaction, the flow of heat is a measure of the enthalpy, so the terms heats of reaction and change in enthalpy are interchangeable. So if you hear heats of reaction or change in enthalpy, these are interchangeable terms. For a chemical reaction, delta H equals the enthalpy of your products minus the enthalpy of the reactants. Right, so maybe this is sounding confusing at this point. It's not too hard. Enthalpy is a state function, which is describes the heat energy in a system. Okay, it's very difficult to measure the heat energy. Well, it's not very difficult at all, but to measure the heat energy of an entire system. But it's perhaps easier, experimentally at least, to measure the change in enthalpy. We can measure this because we know how much a system weighs, and we can measure the temperature change. So delta H is something that's very useful for us. This is our change in enthalpy, and this is given by the enthalpy of the products minus the enthalpy of the reactants. Okay, if the enthalpy of the products, the heat energy of the products, is less than the heat energy of the reactants, then delta H is positive. That means that the heat is being absorbed by the system, and this is endothermic. So if you've got a positive delta H, it's endothermic. If you've got a negative delta H, then it's exothermic. So see, it's very similar to Q in this respect. So it's very similar to heat energy, okay, whether it's endothermic or exothermic. So enthalpy is like our state function for heat. So, right, let's have a look at combustion energy. So when we have a combustion reaction, say we've got some methane, CH4, and we've got some oxygen, O2, and these are our reactants. First, what happens is we're going to have an increase in the energy of the system. Okay, so we're going to need a little bit of heat to start this process. Where might this heat come from? Well, we might have to light a match or use a flame to actually heat up our methane and oxygen mixture. So we need to break those CH bonds, and that's going to use some energy, 1,644 kilojoules. And then, furthermore, we need to break the oxygen bonds. It's going to use a bit more energy. And then we need to form some CO bonds. That's going to use some energy. That's going to produce some energy in this case. And then we're going to produce some more energy when we're forming some OH bonds. And then we've got our products. But overall, we're actually producing more energy than we're using. So it's exothermic overall. And you can imagine that this process can drive itself along, okay, so the amount of energy that's being produced is more than the amount of energy that's being used, so it's going to be like a continuous process until all of the methane and oxygen are used up. So the net energy difference is 802 kilojoules, and we can just add those directly. So this is the way the maths works. It works very simply. We can just add these together, and overall, okay, minus 802 kilojoules. Therefore, it is exothermic. It's giving off heat energy to the surroundings. So let's have a look at the specific heat capacity for the formation of water. Now, if we've got some sodium hydroxide and hydrochloric acid and we mix those together, we can make water and sodium and chloride. So essentially we make water and salt mixture, okay? But something happens, okay? If you measure the temperature of this reaction, so you combine your sodium hydroxide and your hydrochloric acid, it gets warm. So in this case, it's moving from 25 degrees Celsius to 37 degrees Celsius. So we can use this relationship that delta H, our change in enthalpy, equals Cm delta T, where C is the specific heat capacity for water, 4.18, and this is only for water, so every different material has a different specific heat, okay? So 4.18 for water, and multiply that by 100, which is the mass. So the overall mass, so we've imagined we're using 50 milliliters of each, or 50 grams of each, so the mass is 100 grams, times delta T, which is 12, so 37 take 25 degrees Celsius, so 12 degrees Celsius difference, and we can actually work out that our change in enthalpy is 5,016 joules, which is roughly 5 kilojoules. Okay, so that should be a lowercase k for kilojoules. What if we doubled the volume of the reagents? Well, we would just have to double the mass, and that's then going to double the answer. So we'd get 10 kilojoules of energy. Let's now have a look at Hess's law. So since enthalpy is a state function, the change in going from initial to final states is independent of the pathway. We've already covered this. So in going from a particular set of reactants to a particular set of products, we don't care what path it actually takes. So the change in enthalpy is the same, whether it's one step or a series of steps in a reaction. So we could prepare, for example, CO2 as shown above here. So we've got carbon and oxygen gas, and we make some CO2, and it produces 393.5 kilojoules. Or we can prepare it a different way, so we can make carbon monoxide first and then combine that with some more oxygen to make carbon dioxide. But we'll find that if we actually add these together, these two amounts of energy, we get the same 393.5. So regardless of what pathway we take, we actually get the same amount of energy being produced or used by the reaction. Okay, and this is consistent with the first law of thermodynamics, because we can't actually create or destroy any of this energy. It has to come from somewhere. It has to come from the reagents, whether it's bonds breaking or bonds being formed. So the overall process, the energy has to actually come from somewhere. There's no energy for free. So let's take a look at this problem now. What is the delta H for the reaction here? So we've got methane, gas, CH4, plus 2O2 gives us CO2 plus 2H2O, liquid. So we're also given 3 different chemical equations as well, and each of these has a corresponding enthalpy change associated with it. So we've got the first reaction here with an enthalpy change, delta H equals negative 74.81 kilojoules, for example. Okay, so the idea is that we can combine these 3 reactions together, or maybe 2 of them, or maybe a manipulation thereof, to give us the overall reaction. So we need to add these together somehow, in any way that we like, so that we can get our original reaction. So the first thing that you might notice is that we need a CH4 over on the left-hand side. So we need a methane on the left-hand side, but in these 3 reactions, 1, 2, and 3, we don't actually have that available, do we? So we do have a methane, though, in reaction 1. So what we have to do in this situation is reverse the reaction. And when we reverse the reaction, we actually change the sign of our enthalpy change. So our negative 74.81 becomes now a positive 74.81. Okay, now we have 4 reactions to work with, but 3 of these can actually be added together to give us the overall reaction. So 2 and 3, and our new reaction that we've made, let's call it the reverse of 1, or R1. So 2, 3, and R1 can be added together to give us the overall reaction. Okay, now that we've found this to be true, all we need to do is now add our enthalpy values together, and we'll get our overall enthalpy change for the reaction. And the overall enthalpy change for the reaction is going to be negative 890.37 kilojoules. Moving along. Now let's have a look at the topic of standard enthalpy of formation. So this is the enthalpy change accompanying the formation of 1 mole of a compound from its elements. And in this case, all of the substances are in their standard states. Okay, you'll actually have an appendix or a data sheet to go along with this. So this is what was handed out in the lecture. I'll also hand these out in the tutorial as well, but there's selected thermodynamic data from the textbook. We've just gone ahead and photocopied these. This is the data that you'll actually use to work these out. So they're all in standard states. So if it's a gas, it will be 1 atmosphere. If it's a solid or a liquid, it will be pure. And if it's a solution, it will be a 1 mole per litre solution. For an element, okay, it's going to be the form of the element at 1 atmosphere and at 25 degrees Celsius. And this is the following relationship that's used. So the overall enthalpy change at standard state for the reaction is going to be the sum of the standard enthalpy of formation of each of the products minus the sum of the standard enthalpy of formation for each of the reactants. So it's more or less your products take your reactants. You just look them up on the data sheet and you subtract the two values. So in this problem, we need to use our standard enthalpies of formation from the handout to calculate the reaction standard enthalpy change for the reaction shown below. So we've got 4NH3 plus 7H2O gives us 4NO2 plus 6H2O. And the states do matter, so whether it's a gas or a liquid or a solid, because some things, so water for example, is going to have multiple states, okay, and they're going to have potentially different enthalpies of formation for each of these different states. Alright, so it's going to be products minus reactants. So let's look up the standard enthalpy of formation for NO2 gas, and that turns out to be 34, and then for water it's going to be minus 286. I'm going to add those together, then we're going to subtract from that our ammonia. So we've got 4 ammonia, so 4 times minus 46 plus 702, 7 times 0. So notice that if there's a coefficient out the front, we actually multiply the standard enthalpy of formation by that coefficient. Okay, so we end up with minus 1,580, take minus 184, and yet we end up with overall minus 1,396 kilojoules per mole for the reaction. Now we're on to part 2 of, this is thermodynamics now in part 2. So we're looking at spontaneity, entropy, and free energy. So when we talk about spontaneity, what we mean is the reaction spontaneous or not? Will it occur without any outside influence? Okay. If we were to mix 2 reagents together, will the reaction proceed? This is what we're really looking at here. And we need to look at entropy, and we need to look at Gibbs free energy. Okay, this is a bit different from kinetics. Remember when we did kinetics, we were looking at the pathway. So we're looking at, okay, what is the pathway? Can we have a look at reaction orders? And from this, can we then work out the mechanism? So thermodynamics is a bit different. We're just interested at the starting state and the final state of the reactants and the products. And we're looking at the energy changes that are occurring. And from this, we can predict the spontaneity. Will the reaction proceed? What is a spontaneous process? Well, this is a process which will take place without outside interference. So a boulder will roll down a hill spontaneously, but it will not roll back up the hill. It does not necessarily mean fast. Some reactions are rapid, some are slow. They don't have to be fast. Once spontaneous change is initiated, it's going to proceed on its own until some state of equilibrium is reached. So here's an example where we've got an ice cube. Okay, so an ice cube is said to have, in this case, the minimum entropy, the minimum possible entropy, and the maximum order. And over time, it's going to melt into a puddle of water, and that puddle of water has more entropy and less order. What is entropy? We're going to cover this very soon. You can think, at the moment, you can think of entropy as being disorder. Okay? So spontaneous change is towards a condition of greater chance of energy spreading. Now this particular ice cube that we're looking at only has one shape that it can be for it to be this particular ice cube. But our puddle of water, it can have any shape. So as the ice melts, it's not going to take exactly the same shape every time. So there's many more different possibilities for our puddle than there is for our ice cube. The ice cube can only be one way, whereas the puddle can be many different ways. So what determines the direction in which a spontaneous change will occur? One thing that we know is that it's not governed by the energy change. And what this means is that the first law of thermodynamics cannot predict the direction of a natural process. What we need to have a look at is the degree of disorder. So we need a term to express disorder quantitatively. We use S. S stands for entropy, which represents disorder. So S is said to equal K, which is a constant, multiplied by the natural log of W, which is our microstates. And this is where we can use simple statistics to explain what entropy really means. So consider the following example where 4 coins have been tossed. We could get tails, 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 heads, tails, 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 heads, tails, tails, and so on. There's many different possible microstates, we call these, of our 4 coins. These correspond to macrostates as well. So tails, 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 tails corresponds to the macrostate of 0 heads. And likewise, heads, 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 heads corresponds to 4 heads. Now in between, you could have 1 head or 2 heads or 3 heads show up on your 4 coins. Okay? And these have more microstates associated with them. In fact, here we've got 16 microstates in total. Okay? So your chances or your probability of having 0 heads or 4 heads is only 1 in 16. So there's a 1 in 16 probability of having 0 heads. There's also a 1 in 16 probability of having 4 heads, because that's how many of the microstates correspond to that macrostate. What do we see here? Well, in terms of order, 0 heads is a very ordered state. So is 4 heads. But what are the chances of arriving at these very ordered states? Quite slim. 1 in 16 or 2 in 16. What is far more likely is that we'll end up with one of the more disordered states. So disorder is favoured in the universe. That's what we're showing here. Another example that I talked about in class was if you were to take a Rubik's Cube and close your eyes and twist the pieces around, what are the chances of actually solving the cube? Very, very slim, because there's so many more possibilities that are disordered than that one possibility which is order. So the universe has many more microstates of disorder than it has of order. So over time, disorder is going to be more probable. Okay? The greater the number of microstates that correspond to a given macrostate, the greater the probability of that macrostate. So in general, disorder is more probable than order because there are so many more ways of achieving it. Entropy itself is a measure of the degree of the spreading and sharing of thermal energy within a system, and can be considered as a measure of molecular randomness. In chemistry, we consider entropy to be a measure of molecular randomness or disorder, and this is related to the movement of our atoms or molecules. Okay? Because remember, thermal energy is related to this movement as well, and an increase in thermal energy is going to increase these movements. So an increase in entropy of the universe is the driving force for spontaneity. And spontaneous change is towards a condition of the greater probability of the energy spreading rather than being contained. So here's some general statements that we can make regarding entropy in chemistry. We can say that gases have a much greater entropy than liquids, which have a greater entropy than solids. You can see on our graph here, okay, as we increase the temperature, we increase the entropy. But as the solid becomes a liquid, And as the liquid becomes a gas, we have these sudden jumps in entropy because now the molecules are able to move in different ways. So in a solid, they don't move as much as in a liquid. So in a liquid, they're more fluid, they're able to move past each other. And then when we enter the form of a gas, now the gas doesn't even have to stay in its container. It can spread and it can fill the room. It's got more space to go out and be disordered. Okay? So as we warm our substance, we're going to increase the entropy. And as we cross through these phase boundaries, we're going to increase the entropy a lot more. Large complex molecules have greater entropy than simple molecules. Larger molecules have more bonds, more ways to be disordered. When solids or liquids dissolve, entropy increases. Okay, so that's a solid dissolving in a liquid. Now it's got more room to be disordered. When a gas dissolves in a liquid, its entropy increases as well. Okay, for ionic compounds of a similar formula, sodium chloride, potassium chloride, entropy is greater where attraction between cations and anions is weaker. So the stronger the attraction is going to give more order, the weaker attraction is going to give more disorder. The higher the temperature for a particular solid, liquid, or gas, the greater the entropy. Moving along. The entropy of a substance increases with its molecular weight and complexity, with its temperature, and also it's going to increase with decreasing pressure or decreasing concentration. So decreasing concentration, you could think of that as a dilution. So you're taking something that's in a smaller container and you're diluting it with another liquid, and it's going to be able to take up more space and have more microstates. So here's the standard entropy of some substances at standard conditions. So carbon that's contained in a diamond compared to carbon that's contained in graphite, compared to lead, compared to silicon, compared to mercury, compared to oxygen. So you can see that the graphite carbon has more potential to move perhaps and has potentially more microstates. The lead, it's got a larger value, it's got a larger molecular weight. Okay, silicon's intermediate there, mercury has a large value as well. Oxygen, O2, now we're up to 205. Why has this happened? Because now we've got a molecule instead of an atom. We've actually joined two together and now they can vibrate, they can have more of these microstates. Okay, and here's table 2, the entropy of water as we're increasing. You can see it's increasing between a solid, a liquid, and a gas, even if we keep the temperature the same. Let's have a look at the second law in chemical processes. So we know that the entropy of the universe is always increasing, and it can be defined as, so the entropy of the universe can be defined as the entropy of any system under consideration plus the entropy of the surroundings. That's fairly obvious. So a change in entropy of the universe may be represented as the change in entropy of the universe equals the change in entropy of the system plus the change in entropy of the surroundings. Now remember that in a chemical process, the system consists of just the reactants and the products. Everything else is the surroundings. So an exothermic reaction is going to produce heat, and that flows into the surroundings. And it's going to increase the entropy of the surroundings by increasing the random motions of the particles in the surroundings. And conversely, an endothermic reaction requires heat to flow from the surroundings into the system. It's going to cool the surroundings, and it's going to decrease the entropy in the surroundings. Now, as you've probably guessed by now, entropy is closely related to temperature, and we can see it again in this equation here. So the change in entropy of the surroundings equals negative delta H, which is our change in enthalpy, on temperature. So this is our relationship. So the change in enthalpy on temperature, so the change in enthalpy divided by temperature, the negative value of that will give us an idea of the change in entropy of the surroundings. Now, you can calculate the change in entropy of a system in a similar way to calculating the change in enthalpy. Okay, you can have a look at the entropy of the products in the entropy of the reactants, and you can subtract one from the other, and you can get the change in entropy for the system. And again, these are going to be in your appendix as well. So in this problem, we're going to use the relationship delta S naught system, so the change in entropy of the system equals the sum of the change in entropy of the products minus the sum of the change in entropy of the reactants. Moving along now to Gibbs free energy. So Gibbs free energy is the maximum useful work that a system can do on the surroundings when the process occurs reversibly at a constant temperature and pressure. So the Gibbs free energy is defined as G equals H minus T delta S. So Gibbs free energy equals enthalpy minus temperature multiplied by our entropy. So we actually multiply our entropy by temperature because we know how closely related they are. So delta G equals delta H minus T delta S. This will give us the change in Gibbs free energy. If the change in Gibbs free energy for a reaction is negative, so if delta G is negative, then the reaction will be spontaneous to the right. Okay, so if delta G is negative, the reaction as it's drawn will be spontaneous. If delta G is positive, the reaction won't be spontaneous as it proceeds from left to right. In fact, the reverse reaction will be spontaneous in that case. And if delta G equals 0, then the reaction's at equilibrium and the quantities of the reactants and the products won't actually change. So there's two ways to determine the spontaneity of a chemical reaction. So you can have a look at delta S of the universe and see if the system and the surroundings entropies added together give you a positive value. So if we're increasing our entropy, or if we've got a negative value for delta G, Gibbs free energy, we know that it's going to be spontaneous as well. So increasing entropy or a negative delta G is going to tell you that a chemical reaction is spontaneous. And this is summarized here. So here's some equations to remember. The first three are quite easy because they're pretty much the same as each other. And then we've got our relationships to entropy and how that relates to heat, and finally Gibbs free energy and whether or not a reaction is spontaneous. So we want to see our entropy of the universe increasing, we want this to be positive, or our Gibbs free energy to be negative, and it's going to be spontaneous. All right, the end. Thanks for listening.